Section 7.2, the principle of the conservation of linear momentum. So previously, we saw that the work energy theorem, back in chapter 6, led to the conservation of energy. And now we have an impulse momentum theorem. So what might that lead to? I have a hankering we're on the road to another conservation equation. And in physics, if you hear a quantity is conserved, that's a big deal because it gives you a really powerful analysis approach to solving all kinds of problems. So to investigate this, we're going to apply the impulse momentum theorem to the midair collision between two objects. So two things flying through the air and hitting each other. So that's what's shown on the next slide. All right, we have mass 1 and mass 2. They're different. They both have an initial velocity that is downward and towards each other. Then they collide and they bounce off each other and go in opposite directions. Now, before we continue on with this derivation, it's useful to highlight the difference between internal forces and external forces. Internal forces are forces that objects within the system exert on each other. And what we'll see is that internal forces cancel out in terms of the system's view. External forces, meanwhile, are forces exerted on objects by agents outside of the system, external to it, right? So it would be something that's pushing both of the balls, right? If we're focusing on these two balls. Or, as we'll see with these two balls, gravity is an external force pulling on each of them equally. We aren't just going to ignore gravity. So let's take a look now at this derivation. And the details of this are not critical. I just want to briefly highlight where this all comes from. So if you don't like derivations, you can kind of just enjoy it as a storytelling moment. All right, so our impulse momentum theorem, that the impulse is equal to the change in momentum. We're going to do that for both objects, object 1 and object 2, right? Or for object 1, the net force acting on it is the weight of object 1 plus the average force applied that on 1 from object 2. That's during this collision, object 1 feels this huge force to the opposite direction, right? When they crash into each other, they're pushing the other one far apart. So we have that force in here, and that's equal to mass 1 times the final velocity of 1, where this is a vector in 2 dimensions, minus mass 1 times the initial velocity of 1, again a vector in 2 different directions. Object 2, the equation looks almost the same, right? We have the weight of object 2, the force on 2 from object 1, times the time interval over which it happened is equal to the mass of object 2 times the final velocity 2 minus the initial momentum of object 2, mass times initial velocity. Great, what we're going to do is add these two equations together. Why? Well, for 1, it produces some really cool algebra, but for 2, it will help us actually in solving this. So if we add them together, on the left side, everything's multiplied by time, so we can keep that outside. And in parentheses, we'll have the weight of 1 plus the weight of 2 is plus the weight of the force 1 feels from 2 plus the weight that 2 feels from 1. This is where we can take advantage of the fact that the forces that they exert on each other are an internal force to the system, because we know that they're a result of Newton's third law, where every action has an equal and opposite reaction, the way they're pushing on each other. So the force that 1 experiences from 2 is exactly equal to negative the force that 2 experiences from 1. So it turns out these are just going to cancel out, as we'll see on the next slide. Now what do we have on the right side? On the right side, we can do some creative grouping where we're going to group the final ones together, which are both positive. So that's what appears in this first term. And then we're going to group the initial ones, which are both negative, in the second group of parentheses, with the negative maintained between them. So even though we're grouping 1 and 2 things here, this is going to be the total system's final momentum of being mass 1 times final velocity 1 plus mass 2 times final velocity 2. So we can describe that as P final, and then minus, this is the system's initial momentum. This was a lot of condensing down, but let's hang with it just a little longer. It's all going to come together. So what we see here is that because the internal forces cancel out because they're equal and opposite forces, then it's just the weights times the time interval is equal to the change in momentum from final minus initial. And instead of weights, we could make this more general to say it's the sum of the average external forces times the time interval over which they're acting is equal to our change in momentum of the system, where this P final includes both mass 1 and mass 2, same with the P initial. So here we included gravity, for instance, but there are some cases where we don't have any external forces, any net external forces at least, and when we sum them all up. So if the sum of the external forces is 0, then we have 0 is equal to P final minus P initial, or in other words, that our final momentum of the system is equal to the initial momentum of the system. This is a really powerful equation. And it's also known as the principle of the conservation of linear momentum. It's another conservation law. Conservation laws are great. So it says the total linear momentum of an isolated system is constant. In other words, that the linear momentum is conserved. Now, what does an isolated system mean? An isolated system is one for which the sum of the average external forces acting on the system is 0. So you might still have gravity, but if, say, you're supported on a horizontal surface, like the balls are rolling on a table, then we still have gravity acting as an external force, but there's also the normal force supporting it. So that's going to be an average external force summed up to 0. So that's one example there. We're going to be able to apply this to a number of scenarios, because the main one we'll see a lot of actually in the next section, just giving a little bit of a spoiler, sorry, is collisions. Because collisions have a huge amount of internal forces, but internal forces cancel. So as long as we consider the system of both objects, then we're able to say that the momentum before and after is often conserved. All right, let's look at one example. That's not a collision, it's ice skaters, much more peaceful. So starting from rest, 2 skaters push off against each other on ice where friction is negligible. One is a 54 kilogram woman and one is an 88 kilogram man. The woman moves away with a speed of 2.5 meters per second. Find the recoil velocity of the man. So as we're looking at this, we can note, hey, they are both standing there. What are the forces acting on them? Well, we have gravity pulling them down, but then we also have the normal force supporting them. So those two forces are going to balance each other out. So that's not an issue. And the only other forces we have are them pushing off each other. But that push off each other is another internal force to the system of the 2 skaters. So this sounds like an isolated system. Since it's an isolated system, momentum is conserved. We can set our final momentum equal to our initial momentum. And that's exactly what we're going to do here. So let's take a look. So with our final momentum equal to our initial momentum of the system, our final momentum is going to be mass 1 times V final 1 of skater 1, which is the woman, plus mass of the man times the final velocity of the man. And that's equal to 0. Why is it equal to 0? Well, their initial velocity, they're just standing there. You could also set up a problem where they're moving, but perhaps they're ice skaters stuck in the middle of a frozen lake and they're trying to get off the lake. They're stuck not moving. Well, if they push off each other, then they'll be able to start moving, but their initial velocity is 0. So the initial momentum is also 0. So if we want to then solve for the final velocity of the man, the recoil velocity of how he will move in response to the woman moving, we can subtract the woman's momentum to the other side. So we'll do that to both sides. Notice that makes it a negative on the right side, m1 v final 1. And then we'll just divide by m2, and we have this expression for the final velocity of the man. very quick actually. Then we'll plug in the mass of the woman is 54 kilograms times this positive 2.5 meters per second because she's moving in the positive direction, divided by 88 kilograms times the negative sign, comes out to a negative 1.5 meters per second. Right, so a couple things. First, why is it negative? Well, if she's going in the positive direction, the only way we can keep the net momentum constant, keep it overall zero, is if he moves in the opposite direction, in the negative direction, right? So he's moving in the negative direction in reaction to her moving the positive one. The overall momentum is still zero. The other thing to note here is notice how his speed compares to her speed. He's going a bit slower. Why? Well, he has more mass, so he conveys more momentum with a lower velocity, versus if you have a smaller mass, like the woman, you're able to then have more velocity, which, going back to our baseball softball example, the baseball has less mass than the softball, so it's able to have a higher velocity and travel much further. Right, so this introduces the principle of the conservation of linear momentum. Before we wrap up, I want to go over a reasoning strategy. This is taken out of the textbook. So if we want to apply the principle of conservation of linear momentum, what we just did in this last example, but what we'll apply to basically every problem that involves this. First, we want to decide what objects are included in our system. Okay, 2 skaters in our system, 2 balls in our system. Okay. Relative to the system, identify the internal and external forces. Internal forces are things that are just between objects in the system, usually bouncing into each other. External forces are anything outside of what we've defined as our system. Then verify that the system is isolated, that the external forces aren't creating a net external force on them. If it is indeed isolated, then we can set the final momentum of the system equal to its initial momentum. We do need to remember momentum is a vector, so the directions do matter here. Unlike energy, where we said, direction doesn't matter, speed is speed, this is now velocity with a direction. So hang on to that, and you will be in great shape to be approaching solving these problems. I'm happy to help as you have questions. Otherwise, let's continue on.